In this video, I'll show how memory is managed inside a computer system. In normal operation, a computer system has many programs stored in the memory at the same time. But how can that work? Which program gets to run? How can one program avoid overwriting another? So far, we have assumed that there's only one program in the memory at one time, and that program has access to all of the memory from address 0 to the end. If we have more than one program in memory, who decides which program to execute? How do we stop one program from accessing the memory space of another? How does a program know where it starts and where its data is stored? How do these programs coexist? But first, a disclaimer. The hardware of a modern CPU is very complicated. We've had more than 70 years of evolution of hardware design and implementation, leading to super powerful but super complicated systems. To help you understand, I need to start with simple ideas and build on them. So for this reason, the structures I describe are the basic, simple ideas, but not exactly what we use today. But don't worry, this will help you understand the basics, and we'll get to the more complicated structures in a later CS tutorial. So back to our question of how do we make more than one program coexist in the memory at the one time? The answer is a combination of hardware and software. Hardware to protect the memory space of one program from another, and software, the operating system, to decide which program gets to run and for how long. Usually, programs have access to memory starting from address 0 to the end of the memory, but they can't all be located at address 0. So this is achieved by having special hardware in the CPU that remaps the address space for each process when it's running. This address mapping hardware translates all references to memory from one location to another. This is done by the CPU having a special register that contains the base address of the running program, where that running program starts somewhere in the memory. When a program accesses memory, the contents of this register is added to the address that it wants to access. This means that, of course, the program can't access any physical memory address before the base address. And the reason for that is that all memory addresses must be positive. They can't be negative. So your program can only access addresses starting at the base. For example, if your program addresses address 0, it'll have the base address added to it, and so it will actually address whatever the base address is, and so on. And so it remaps those addresses into the new address space. In addition, there's another register that puts an upper limit on the addresses that the process or the program can use. This prevents the program instructions from accessing beyond its allotted memory area. The running program is then confined between the base address and the limit address. These special registers, the base address and the limit address, have to be controlled by a privileged program. Otherwise, your program could just change them and therefore access all of memory. That privileged program is actually part of the operating system. It's called the operating system kernel. Since these special registers can or should be only accessed and changed by the kernel program, we need a mechanism to distinguish between the operating system kernel and other application programs. This is done by having two operating modes in the CPU. One is called user mode, and that's where your programs run, and the other is system mode, and this is where the operating system kernel runs. When in the system mode, the kernel can access the special base address register and the limit register and various other registers that are restricted to the operating system. Whether the CPU is in system or user mode is indicated by a single bit register. When that bit is set, the running program, the operating system kernel, has access to more parts of the CPU. A very important function of the operating system kernel is to decide which program to run. To switch between the user mode and the system mode, we use a feature of CPUs called an interrupt. Now, an interrupt is where a currently running program is interrupted and all of its state, that is the memory, the CPU registers and other information about the program, is saved. The user system mode bit is then set, indicating that we're back into system mode, and the kernel program is started. Later on, the kernel program can restore the state back to what it was for that program and restart the program. The program will then continue as if nothing had happened. An interrupt is completely transparent to a running program. When the program is restarted, it has exactly the same state as before the interrupt, and it can't detect, in most cases, that it was interrupted. Interrupts can occur when various things happen, such as an input-output device needing attention. Someone types a key on a keyboard, then that device needs attention. CPUs with user and system mode also have a clock, a simple counter that counts up every millisecond, for example, and it can be set so that an interrupt occurs periodically. For example, it might count down to 0 and then the interrupt will occur. Then the operating system can reset it to a large number, and when it counts down again, the interrupt will occur. And so it always regains control when a certain time has elapsed. Now, when an interrupt occurs and the operating system kernel gains control, it, as I said, saves the state of a program and does something on its behalf, but then it doesn't have to restart that same program again. It might restart a program that it saved earlier. So it, in effect, switches from one program to another. And this is how CPU time is shared between programs. The kernel can also gain control by a program explicitly calling the kernel using a special system call instruction. This is how your program requests services from the operating system. Services such as opening and reading or writing files, or making a network connection, or something like that. The system call operates in a very similar way to an interrupt, except it also passes some parameters to tell the operating system what service to perform. The combination of the memory occupied by the program and all of its state, so the registers and any other information about the program that's held by the kernel, is called a process. Now, in the Unix operating system, we usually have a large number of processes that are in memory and available to run at any one time. Of course, on a single CPU, only one program can run at a time, but modern systems have multiple cores, and so they can run several programs simultaneously. On a typical small Unix system, you might have as many as 150 processes, in other words, 150 programs that are all in the memory at the one time and in various stages of execution. I'm going to talk about processes in a video all by itself because they're so important, where in that video I'll describe the memory layout of a process and how they're managed and so on. CPU scheduling, how we decide which one to run next, and so on.